Now that we have a bit of practice developing recursive functions, let's do a comprehension problem to make sure we all understand what's going on here. So I've got a notepad to keep track of what we're doing, and let's see what's in the code. So we have two functions defined, foo and bar, and then in the global space it says z equals foo of 4. So I'm going to go ahead and create a global scope, and inside that scope I'll say z equals, but before we know what it equals, we have to first evaluate this call of foo of 4. So to do that, we call that function, which means create another scope for that function. So we call this function foo with the value 4. That has a parameter called y, so we say y equals 4. Now I'm also going to keep track of the line numbers in these scopes, just so that we know where we left a certain scope. Because you can see we have a bunch of function calls. We have foo calling bar, and bar calling foo. So in order to keep track of where we are and where we're going back to, let's also keep track of our line numbers. So in global, we called foo from line 14. So we jump down to foo, and then we're at the top of foo, so we could say we're on line 1 right now. All right, then on line 2, it says if y is less than 4, which is false, so we jump down to line 4, and it says return bar of y times 2 plus 1. So in order to evaluate this expression, we have to first call bar, so we create another scope, so we say bar. So we're on line 4 when we call bar, we jump down to line 6, and that creates another variable called x that gets our value, which gets the value of our argument, which was y times 2. So y was 4, 4 times 2 is 8, so x equals 8. And now notice we have separate line numbers for each of the different functions we're in, because we need to keep track of where we were when we made the call that left that function scope, so that when we go back to that function scope, we can continue on where we left off. So while we're in bar, on line 6 we could say, at the top there, we created our variable, we go on to the next line, line 7 says if x is less than 10, that's true, so we go down to line 8, and that says return foo of x minus 2. So we make another scope. So we call foo again. Now I'm going to call this foo prime, just so we can distinguish between the two, because notice we haven't finished resolving this foo. So if this notepad is keeping track of the call stack, which it more or less is, we're going to have two instances of this foo, two frames as they're called, on the call stack, representing independent instances of this function call. So this is foo prime, and it has a variable called y. When we were on line 8, we called it from bar. So on line 8, we said foo gets the value of x minus 2. So x is 8, so 8 minus 2 is 6. So now y equals 6. So notice in the two different instances of foo, we have two different copies of this y variable. They're stored in different spaces in memory. So they have independent values, independent existences. Okay, now we're at the top of foo, so we're on line 1 again. That says create this variable, and then go on to line 2, which says if y is less than 4, that's false still, so we go down to line 4 and say call bar again. So bar single prime has a parameter x, which gets the value y times 2. So 6 times 2 is 12. And then we continue on with bar from line 6, the top of its definition. Creates our variable, go to line 7. Is x less than 10? That is false. So we go down to line 9. Is x equal to 12? That just so happens to be true. So we go to line 10, which says call foo with x minus 2. So we create another instance of foo, another frame on our call stack, where foo's variable y is equal to, bar from line 10 says just pass in the value of x, so 12. All right, so inside foo, we're now on line, we'll say 2. We ask, is y less than 4? That's false, so we go down to line 4, and we make another call to bar. So bar double prime has a parameter x, which is equal to y times 2, so 24, and we're at the top of bar, so line 6. We enter that function, we say, is x less than 10? That's false, so we go down to line 9. Is x equal to 12? That's false, so we go down to line 11, which is an else, which pushes us on to line 12, at which point it just says return 0, no more function calls. We've reached a base case, so to speak. So when we return 0, let's put an arrow here, this returns 0, and that means go back to the function that called us, so that's just one step up this stack, at line 4, and take this value with you. So we take the value of 0 to line 4 where we called bar. and that's here. So this whole call here now equals 0. And that says return 0 plus 1. So we left this. We're still on line 4. This part of the expression, the function call, now has a value. We said at return the value 0. So we say 0 plus 1, and then this returns 0 plus 1, which is 1. And that goes back up to here. So this disappears from the call stack, and we're on line 10. So here, where we said foo of x, and we passed in the 12. So this section here, foo of x equals 1, and now we say return 1 minus 2. So this returns 1 minus 2, which is negative 1. And now all this gets removed from the call stack when it returns negative 1 to line 4. So negative 1 plus 1 gives us 0. So all of this is gone, and this returns 0. So negative 1 plus 1 gives us 0. That returns back to bar. So foo was called from line 8 inside of bar. So if we go to line 8 inside of bar, that just says return whatever foo returns. So if foo returns 0, that means this will return 0 as well. So that disappears off the stack. So if this returns 0, it returns to its calling function, which was foo at line 4. So we have this call here is 0 plus 1. So when this disappears, we're on line 4. And this returns 0 plus 1, which is 1. And if that's returning, it returns to line 14 in the global space, which is where we called foo of 4. So all of this disappears, and in our global space we get z equals 1. And if you had an output section, we'd have our first output there, which just says print z, which has the value of 1. So be glad that we have a computer to keep track of all of this for us. We don't normally have to do this manually, but it's a very good exercise to put your brain through the task of trying to keep track of all of it, just to make sure you understand what the computer will be doing with this information. But this is the idea behind recursion. Every time we make a function call, we're adding an instance of that function to the call stack, and the call stack is going to keep track of all the tricky returns and all this for us. All we have to know is each time we're making a recursive function, we want to have a base case, so our recursion ends eventually, a recursive case to actually power that repetition, and something in that recursive case that shrinks it so we get to the base case. Notice we had all that here as well, although the problem itself wasn't super clear, so there was no solving some single thing, but our base case we could say was line 12 here, where we return 0, and our recursive cases, in this case we have two co-recursive functions because they're calling each other. Notice foo never called itself, but foo calls bar, and bar calls foo. So together these two functions are recursive in terms of an overall process. So recursion is not just when a function calls itself specifically, but when the process of executing that function results in another call to that same function. Right? So before I can resolve what the value of this foo of 4 was, that called bar, which eventually called foo again. So indirectly recursive, you might say. Okay, hopefully all that made sense. And if not, it was all recorded, so you can just rewind and watch it again. And if that doesn't help, feel free to reach out. I'm always happy to talk about this stuff. But that's it for this video, so I will talk to you in the next one.